there. Yeah, like Addison mentioned, feel free to put in your questions in the chat. So now we're gonna head back over to our AIMS presentation from the Louisiana Water Resources team. So I'll go ahead and let them take it away.
Thank you so much, Ryan. So hi, everyone. Thank you so much for taking the time out to be here. My name is Mariam Moeen, and I'm the project lead for the Louisiana Water Resources team here at AIMS. And today, actually, before I get started, I wanted to go ahead and introduce the rest of my team, which includes Daniel Babin, who's our data manager, Kelly Young, Taryn Waite, and Tasos Tentoglou. And today our team is going to be walking through a Google Earth Engine tool we developed, which assesses the extent of seagrass meadows in the coastal Louisiana region, and also studies how the barrier islands in the region have changed over time. Next slide, please. So this is a map of our study area, which shows the Breton National Wildlife Refuge and its surrounding coastal areas. Breton National Wildlife Refuge is located off the southeastern coast of Louisiana and was established in 1904. It's the United States' second oldest national wildlife refuge and consists of a chain of barrier islands between the coastline and the Gulf of Mexico, which includes the Breton and Chandeleur Islands. We've also included a true color image on the right-hand side, just so you can get a better idea about what these islands look like close up. And I just wanted to note that these islands are ever-changing and are shaped and reshaped by currents, storms, and other dynamic ocean processes. So I'll go ahead and hand it off to Kelly to go into a bit more detail about the background of this study region. Next slide, please.
Thank you, Mariam. And to provide some more background information, the Breton National Wildlife Refuge consists of a series of barrier islands that protects the coastline of Louisiana from destructive storm surges. The islands are of importance to conservation efforts because they provide crucial habitat and nesting grounds for several bird species. In the shallow water surrounding the western shore of the islands, seagrass beds support a biodiverse marine ecosystem. Seagrasses are types of submerged aquatic vegetation, and along with supporting biodiversity, they also provide essential ecosystem services to Louisiana's coastal community. By absorbing excess nutrients in the water, seagrasses help prevent harmful algal blooms that can cause fish die-offs. By providing marine habitat, the seagrass beds also benefit local fisheries. And lastly, seagrasses trap suspended sediment and help to reduce erosion of the barrier islands, thereby contributing to storm surge protection. Next slide, please. There are a few factors that impact the health of seagrasses and the barrier island system. Firstly, hurricanes are known to destroy land area. In 2005, Hurricane Katrina reduced land area by upwards of 80%. Secondly, events such as oil spills, particularly Deepwater Horizon in 2010, reduce habitat for seagrass, which can impact their annual extent. In addition, sea level rise and anthropogenic climate change are examples of ongoing threats to the area and can increase storm frequency and severity, which speeds up the loss of land. Ultimately, this creates the cyclical function seen on the right. As storms reduce land area, it also takes habitat away from the seagrass beds, which cause them to shrink. And as seagrass beds shrink, island protection is decreased, which speeds up erosion and land loss. As long as this cycle continues, both the barrier islands and the seagrass are left vulnerable. Next slide, please. Here you can see some of the water quality indicators that impact seagrass health. Salinity measures the amount of salt in the water and is impacted by varying levels of freshwater inputs from the surrounding area. If the salinity is too high or too low, seagrass growth can be stunted and mortality can increase. Turbidity measures a relative water clarity, which is impacted by suspended sediment. Turbidity can be influenced by island erosion and reduce the ability of light to penetrate the water. Thus, as the islands continue to erode, turbidity increases, which reduces light availability and impacts seagrass growth. Lastly, chlorophyll refers to a green pigment found in vegetation. It can be used to measure harmful algal blooms, plant life, and even seagrass. In the case of our project, chlorophyll can be nutrient dependent and thus potentially be correlated to phosphorus and nitrogen concentrations in our study area. Next slide, please. I'll now talk a little bit more about restoration and revegetation efforts. The images on the left show the drastic decrease in land area of the Chandeleur Islands between 1984 and 2019. In 2020, a major restoration project began to rebuild the islands and their habitat suitability. Seagrass beds off the coast of the islands will be restored using methods such as transplantation and recolonization. However, in order to choose optimal sites for seagrass revegetation, restoration experts need to understand historical trends in seagrass bed locations and water quality parameters. This is where our project comes in. I'll pass it off to Tasos to talk more about our project specifics.
Thank you, Kelly. You can move on to the next slide. So the main project objectives were geared to address community concerns regarding the shrinking islands and seagrass meadows within the Breton National Wildlife Refuge region. So first, our team developed a Google Earth Engine tool that monitors and evaluates water quality parameters in the study area. Users of this tool will be able to analyze historical trends in water quality parameters, which are relevant to the seagrass health. And finally, users will have the ability to generate maps which display current turbidity conditions and seagrass bed locations. Next slide. So our tool uses Collection 1 Tier 1 surface reflectance data from Landsat 5's thematic mapper, Landsat 7's Enhanced Thematic Mapper Plus, and Landsat 8's Operational Land Imager. And though each of the satellites' date ranges overlap with one another, the data sets were pieced together in a continuous manner, which is shown below in the timeline. Landsat 7 had actually malfunctioned 4 years into its launch, which resulted in major gaps to appear in the imagery. And for this reason, we tried our best to avoid using Landsat 7 data and instead use Landsat 5 to cover the majority of Landsat 7's temporal range. Then we switched to using Landsat 8's data once it was launched. So Landsat satellites have a temporal range of 16 days, and they have a spatial resolution of 30 meters. And this data was processed through the cloud computing platform called Google Earth Engine. Next slide. So for processing the data, we masked out clouds, cloud shadow, and land from the images to improve the accuracy of our data results. And this was done through Landsat 5, Landsat 7, and Landsat 8's pixel quality assessment bands, which are also known as pixel QA bands. And these pixel bands easily identify which pixels have cloud impurities or land cover. So looking at the right-hand side, the image to the left is unmasked, and the image to the right has lands and cloud masked out of it. Next slide. So the first parameter our tool assesses measures seagrass using the normalized difference to aquatic vegetation index, which is also known as NDAVI. Photosynthetic organisms reflect a large amount of near-infrared light, and through comparing the amount of near-infrared light and blue light, this index can be used to measure the relative seagrass abundance within the Chandelier Islands. Next slide, please. The second parameter our tool assesses is turbidity, and as Kelly mentioned before, this refers to an optical characteristic of water, which is measured by the amount of light that is scattered with the material in the water. So the higher the intensity of scattered light, the higher the turbidity is. Material that causes water to be turbid include clay, silt, algae, dissolved colored organic compounds, and other microscopic organisms. So this will cause the water to be cloudy or opaque. So comparing the amount of red and green light can bring the amount of suspended sediment in the water. This means that turbidity can be measured through the normalized difference turbidity index, which is also known as NDTI, and this uses the red and green bands for analysis. Next slide. The last parameter our tool assesses is chlorophyll alpha, and as mentioned before, photosynthetic organisms reflect a large amount of near-infrared light. However, for this index, we compared the near-infrared band and the red band to analyze chlorophyll or algal blooms within our study area. And this is where the normalized difference vegetation index was applied and calibrated with this equation below to determine the chlorophyll alpha values, which is also the NDCI index. I will now pass it off to Taryn, who will go more in depth on our Google Earth Engine tool and its extended capabilities.
Thanks, Tasos. Next slide, please. The tool for coastal remote ecological observations in Louisiana, or tool CREOL, consists of an interactive user interface in Google Earth Engine. We created tool CREOL in order to fulfill our partners' needs to both understand historical trends in seagrass extent and water quality, and also to monitor conditions both today and moving forward. As shown here, users can choose one of the several areas of interest to examine within the Chandelier Islands region. They can then select any year and season since fall 1984 and add their choice of imagery to the map. This imagery includes true color, the spectral indices representing seagrass and turbidity, chlorophyll A, as well as sea surface temperature. and they can also view a land-water classification for the region of interest. Users can also generate time series charts displaying the overall variation of a parameter within the region over a chosen time period. Next slide, please. In addition to the basic imagery and time series functions, our tool also includes some special features to help our partners further understand spatial and temporal variation of seagrass beds and water quality parameters. So first, the slide comparison feature allows users to dynamically view two images side by side. This feature can be used to compare two different parameters from the same year and season, as is shown on the left with true color and turbidity. Users can also compare images from different times if desired. And then Tool CREOL also includes a point change inspector, which allows users to examine temporal variation of parameters at specific points throughout the region. So the example shown on the right displays a plot of the seagrass index from 2010 to 2020 at the location marked by the red circle, which was selected by the user on the map. The point change inspector allows for a more nuanced analysis of the spatial variation in historical trends. And I'm going to pass it on to Daniel to talk about some of the results we were able to generate using our tool.
Hi, Taryn, thanks. Yeah, so here's what you've all been waiting for, the data from Tool CREOL. So earlier, Kelly made the claim that storms, hurricanes, are detrimental and threaten the Chandeleur Islands. And so this figure was generated to test that claim. We produced imagery from the tool. So here's spring 1984, and on the far right side is spring 2021. This represents the entire duration of our study interval. And in the middle panel, there are 6 different time series. We used the point inspector to make 5 time series in a latitudinal transect of the normalized aquatic vegetation index. And we also generated across the entire study region a land area calculation. So this just compares the number of water pixels classified to the number of land pixels classified and calculated in terms of kilometers squared. And over these 6 parameters are overlaid the dates of hurricanes. So you can see in the earlier part of the record, there's storm events, Andrew and Josephine. They have a clear impact on land area, less of an impact on the normalized aquatic vegetation index. But somehow the land area is able to respond more rapidly. But following Hurricane George, Ivan, and Katrina, we see a lot of land loss in the Chandeleur Islands, going from about 16 kilometers squared in the year 2000 to about 2 kilometers squared in the year 2005. So that's about an 80% loss in land. You can see that aquatic vegetation suffers with the Ivan and Katrina hurricanes. It's either spelling the end for the seagrass beds there in the northern part, or kind of the beginning of the end, leading to a gradual decline in these more southern records. You might look at this bar and wonder why the BP oil spill could contribute to land growth in the islands. We wondered the same thing. So research yielded, though, that a sand berm, which is kind of a wall of sand, was constructed around the island in an effort to protect the seagrass and other ecosystems on the island from the oil intruding. And you can see that there's actually even positive feedbacks associated with this that contributed to land growth over the coming decade. And I think this is important because it highlights the potential long-term value benefits of restoration projects, such as the ones that our partner has planned. Next slide. This figure was made to understand how seagrass in the Chandeleur Islands is responding to freshwater or saline conditions. So what is the environmental sensitivity of seagrass? And so this is on the top, the green panel here, or the green time series, is showing you normalized difference aquatic vegetation index average across the entire Chandeleur Islands across the duration of our study. And then the blue panel is Mississippi River discharge. So the Mississippi River should be the largest freshwater source. It's integrating river runoff and precipitation from across the entire Mississippi River basin. At the bottom is a model of salinity, and ideally these two should be following each other, given that the Mississippi River is the largest source of fresh water. And so Visual inspection yielded that there's a positive relationship between the strength of the aquatic vegetation index and Mississippi River discharge. So that would be that fresher conditions promote more healthy seagrass. Next slide. Another thing we wanted to test was related to the algal blooms. So phosphorus in this case, this is a data set from the Army Corps of Engineers, is runoff from agricultural land in the Mississippi watershed. And you can see that over the past few decades, it's been increasing. In the same way that we generated that time series of NDAVI, we made a time series of chlorophyll. I see some claps. And you can see that chlorophyll concentrations are increasing across our study interval as well. And I think there's quite a good match between these two time series. It both gives us confidence in the quality of our analysis and a way to monitor these algal blooms in an ongoing way. Next slide, please. So these are finally some static images from the map. This is turbidity. You can see in general, there's some patterns around the islands. Here, lighter colors, more yellow colors are more turbid water. You can see that in general, closer to the islands where the waves have more energy to resuspend sediment, the water is more turbid. But this pattern likely varies seasonally. That could explain some of these differences, perhaps between 2000 and 2005. But something that's profoundly comes across here is the difference in land area between 2000 and 2010. I mean, the land is basically scraps by that point. But this highlights the destructive impact of the hurricanes. You can also see some issues in 2020. I think this is a good example of some kind of problematic aspects of our tool caused by clouds. And Taryn's going to talk more about that and other issues.
Next slide, please. Thanks, Daniel. So I'm going to just be talking about several factors that limited our ability to obtain consistently accurate results across our time period. So first, as Daniel just mentioned, the high frequency of heavy cloud cover in the region, particularly during hurricane season, meant that we had to mask significant portions of many of the images we used. And this led to some really patchy imagery for some years and seasons, as shown in the examples to the right. So the way these images are displayed is that we have the least cloudy image shown on top, and then more cloudy images kind of layered underneath to fill in the gaps. And so that's what causes that patchiness in times when there were a lot of clouds. Additionally, the differences in parameter intensity between seasons introduced some challenges in our choice of visualization parameters for the tool. And then a source of uncertainty in our time series analysis was the inconsistencies between the sensors used by the different Landsat missions. So particularly the differences in the wavelength ranges that were measured by Landsat 5's near infrared band compared to Landsat 7 and 8. Additionally, we didn't have access to sufficient in situ data to properly validate all of our tool's results. And then finally, our chlorophyll calculations may not have been fully accurate because, as Tasos mentioned earlier, we used the normalized difference vegetation index in place of the normalized difference chlorophyll index in our calculation. And this was due to constraints in the wavelengths measured by the Landsat sensors. So I'm going to pass it off to Mariam to state some of our conclusions.
Thank you, Taryn. So looking at all of the functionality within the tool collectively, we believe our partners will be able to use tool CREOL to better understand historical trends and spatiotemporal variation in both seagrass extent and water quality around the Chandeleur Islands. As the tool automatically uses the most up-to-date available imagery, our partners can also continue to use the tool moving forward. And these capabilities will be of great use for the restoration and revegetation project that began in 2020 and future restoration efforts as well. Next slide, please. So after looking at various water quality parameters through time series distributions in conjunction to the imagery, we noticed that there was tremendous land loss from hurricanes Georges, Ivan, and Katrina. Overall, we observed the seagrass ecosystem deteriorated along the Chandeleur Islands. There were some restoration efforts that were implemented in the coastal Louisiana region to restore the damage from destructive events such as the oil spill. Additionally, a sand berm was constructed in 2010, which had a positive and lasting impact on land and seagrass health. We noticed the Chandeleur Island seagrasses thrive in less saline conditions, Additionally, algal blooms have also increased continuously since the early 1990s. Next slide, please. So future work includes incorporating Landsat Collection 2 data into the tool, utilizing in situ data to provide validation for our imagery, and adding a GIF generator panel into the tool. So incorporating Landsat Collection 2 data would provide the most up-to-date and accurate imagery in our tool. We previously actually attempted to incorporate this new data set into our tool, but then ran into multiple processing errors that made the data difficult to use. Additionally, very little in situ data was available for our study area parameters. Obtaining data for chlorophyll, turbidity, and SAV would improve the tool CREOL's accuracy and provide validation for the results that we acquired through the tool. Lastly, we really hope to add a GIF generator to our tool. We really believe that the addition of this generator would provide additional usability for the user and also for the creation of GIFs to model changes in our parameters over time. And this would be very useful for a broader audience as well. Next slide, please. So before we end, we would really like to give a sincere shout out and thank our partners for collaborating with us on this research project. So we had partners from the Louisiana Coastal Protection and Restoration Authority, Greg Grandy, Todd Baker, and Kenneth Ballinger. We also had partners from the Louisiana Department of Natural Resources, Mark Hogan and Sarah Krupa. So a huge thank you to them. And then, of course, we would like to thank our science advisor, Dr. Juan Torres Perez, for his invaluable guidance and input throughout this project. And a huge thank you to our mentor, Brittany Vaudry, for all of her contribution, all of her input, and all of her guidance throughout this term. And yes, next slide, please. So these are our references, and thank you so much for taking the time to listen, and we will take any questions.